This is the experimental data for the Beer's Law experiment, Principles of Chemistry 1. In this experiment, we're going to change things from the original protocol in that we're going to be using cranberry juice instead of water with green food coloring. We'll assume that the concentration of the cranberry juice is initially 0.450 molar, unlike the lab handout that claims a different number. You will use 0.450 molar cranberry juice. Vials of different and known concentrations, otherwise known as standards, will be prepared from this stock cranberry juice. And then a colorimeter is going to be used to measure the absorption of each of the standards to create what is known as a Beer's Law plot. It's a calibration curve that we'll be able to use to determine the concentration of an unknown at the end of the experiment. As we prepare standards, we're going to use the 0.45 molar cranberry juice and we're going to combine it with distilled water. We'll use 2 burettes labeled in the picture that you can see to dispense known amounts of distilled water and cranberry juice. All of the standards will be prepared in the vials that you see off to the right-hand side. The standards are prepared by first adjusting the burettes to read 0. In the left picture, you'll see the cranberry juice. This is undiluted cranberry juice, 0.450 molar, and the meniscus has been adjusted to read 0. In the right-hand picture, we have the burette that's been loaded with distilled water, and it too has been adjusted to read 0. As we continue preparing standards, we are going to first address water. And in this first measurement, we're going to measure out approximately 2 milliliters of water and add that to vial 5. Now, I say approximately. It's up to you to examine this picture, and knowing the initial burette measurement was 0, and looking at the meniscus now, in this situation, make a measurement of the water level, keeping in mind that burettes read from the top down, and that all burette measurements must have 2 decimal digits. This measurement is not 2 milliliters. You need to do a better job of measuring it by examining the picture and deciding just exactly how much water has been added. This idea will extend to the following series of water additions. Let's move on to vial 4. In vial 4, approximately 4 milliliters of water will be added, and the burette, as you can see, is near the 6 mark. Well, it was near 2 previously, and now it's near 6, and so approximately 4 milliliters has been added. You'll need to use the before and after measurements, both done with 2 decimal place accuracy, to determine the actual amount of water that has been dispensed into vial number 4. Similarly, for vial number 3, we've added approximately 6 milliliters of water. Make this burette measurement and use the previous burette measurement to determine exactly how much water has been added to the vial, 3 in this case. Remember, we must use 2 decimal place accuracy for all burette measurements. Moving on now to vial number 2, approximately 8 milliliters of water has been added. Again, the same procedure as in the past. Make the burette measurement, record that on your data sheet with 2 decimal place accuracy, and prepare yourself to subtract numbers to determine exactly how much water has been added to vial number 2. It should be something close to 8 milliliters. At this point now, we've got all of the water that needs to be dispensed in these 6 vials. Vial number 6 will eventually contain the pure, undiluted cranberry juice. That's what we'll call vial 6. Vial 5 has approximately 2 milliliters of water, and then as we move from left to right, vial number 2 has approximately 8 milliliters of water. To these vials, we are going to next add cranberry juice from the second burette. We'll address vial number 2 first. That's the one with approximately 8 milliliters of water. To this, we're going to add approximately 2 milliliters of juice. So make the burette measurement and determine how much juice has actually been added to vial number 2 with 2 decimal place accuracy. After mixing the vial very fully, we have there in the lower right-hand picture our final vial 2 prepared. As you can see, it's quite light in color, and of course that's because there's quite a bit of water for the amount of juice that was added. Let's move to vial number 3. Vial number 3 is going to see approximately 4 milliliters of juice. And you've got the burette there. You can make your measurement. It'll be well mixed. And in the lower right-hand corner, you can see vial number 3, slightly darker than vial number 2. No surprise, as there is 4 milliliters of juice to about 6 milliliters of water. Of course, you'll need to record those numbers with 2 decimal place accuracy. In vial number 4, again, things are getting more concentrated. The approximately 6 milliliters of juice are added, and the burette measurement, just a little crooked there, do the best you can, but record that volume and determine the amount of juice that's actually been added to vial number 4, and you can see it there in the lineup in the lower right-hand corner. Moving on to vial number 5, the last of the vials that we'll construct from a dilution process. Here we add approximately 8 milliliters of juice to the 2 milliliters of water that were there. Read the burette, determine exactly how much juice has been added, and we can move on to the lineup. Now, in this slide, you can see that I've actually put undiluted juice into vial number 6. And as they are ordered from vial 6 to the right, vial 4, 3, 2, you can see them getting lighter and lighter as they are becoming more and more dilute. Their exact concentrations you'll calculate using the dilution equation as part of your lab write-up. What we hope to do here is we hope to determine just where exactly an unknown would be positioned, having more concentrated solution to the right and less concentrated solution to the left. Let's have a look at how that might appear. I'll go ahead and pour some unknown liquid into another vial so that we can determine where it belongs. Now, in this slide, I've positioned the unknown at the far left-hand side, and the question is whether or not that seems reasonable. You may want to zoom in on this by zooming your browser window, but our goal is to figure out whether our unknown really belongs to the left of vial 6, which is to suggest that it is more concentrated than vial 6. Or, if you prefer, maybe it should be between vial 6 and vial 5. You be the judge. We are looking to determine with our eye, to the best of our ability, where this unknown belongs. Is it between vial 5 and 6? Or is it between vial 4 and 5? Or between vials 3 and 4? Or between vials 2 and 3? Or perhaps it really needs to be off to the right entirely. Now, I think you can probably see that that isn't correct at all. It's quite a bit darker than vial number 2 and doesn't belong on the far right-hand side. Rather, it belongs to the left in that order someplace, and you should do your best to determine where you think it should be. There is no right or wrong answer. Do the best you can to eyeball this. Now that we have our solutions constructed, we need to go about the business of using the colorimeter to determine the percent transmission for each of these solutions. As part of this procedure, we'll need to clean the cuvette. The cuvette is the little rectangular box that you see there. It has clear windows on one side and ribbed windows on another. And then we're also going to place we're going to place distilled water in that cuvette 3/4 of the way full and then reapply the lid, as you can see in the rightmost photograph. Then we're going to open the calorimeter. That's the upper left-hand picture. We're going to insert the cuvette into the calorimeter, upper right-hand position, close the door on the colorimeter. Very important thing to do because we do not want external light to confuse this measurement. And then we'll press and hold the calibration button. This is to instruct the calorimeter, to calibrate the calorimeter, so that it knows what plain, ordinary water looks like. And water, as it has none of the cranberry juice in it, should transmit 100% of the light. Now, these colorimeters are pretty good instruments, It's very rare, however, that water all by itself comes out to be exactly 100%. And the 99.91% you see here on screen is a perfectly acceptable value for a calibration. At this point, we can now move on and begin testing our solutions. We'll rinse the cuvette with a small amount of solution number 2. We'll insert the cuvette into the colorimeter and close the door. The computer display tells us what the percent transmittance is, and in this case, vial number 2 has a percent transmittance of 64.52%, and this is a value you should write down corresponding to solution number 2, vial number 2. Moving on to solution number 3, again, we rinse the cuvette. We're working in the order of increasing concentration to avoid issues associated with cross-contamination. It's always better to start with dilute solutions and work your way in the direction of more concentrated solutions, rinsing along the way. Now, when solution number 3, or vial number 3, is put into the colorimeter and the door closed, the transmittance goes down to 41.50%. This just makes sense because this solution has more cranberry juice in it and therefore should let less light through it. Solution number 4 continues this trend. We rinse the cuvette, put the cuvette into the colorimeter, close the door, and for solution number 4, the percent transmittance is 26.16%. Solution number 5, again, the numbers continue to drop. For solution number 5, the percent transmittance is 14.59%. We finish up the measurement of the standards with solution number 6. This solution is a solution which contains the undiluted cranberry juice. It's the darkest red of the bunch. And when we clean the cuvette and insert it into the colorimeter and close the door, the transmittance takes on its lowest value of all at 9.31%. This just makes sense. This is the darkest, reddest solution that we have, the most concentrated cranberry juice sample that we will test, and it transmits the least light. To finish up, we have an unknown. And this unknown is treated in exactly the same way. The cuvette is rinsed slightly and then filled to the 3/4 mark with the unknown solution. It's put into the colorimeter, the door closed, and in this case, this unknown gives us a percent transmittance, which is 23.46%. With this information now, the percent transmittances from the standard solutions, their volumes used to calculate concentrations, and the percent transmittance of the unknown, you should now go on to do your calculations, create a Beer's Law plot, and eventually determine the concentration of the unknown solution to 3 significant figure accuracy.